This is the 4th EAGE newsletter for April 2022, and in today's newsletter we'll cover what Jensen Huang is saying about the future of AI, and then learn how transformers work as well as compare to convolutions, and then we'll go over a very interesting data-driven solution for weather model, as well as we'll touch on unsupervised machine learning applied for seismic interpretation, and we will end up with the code that you can run on your computers for first break picking. As you understand, we are trying to cherry pick very interesting topics within the AI/ML universe and condense it to this AI newsletter. So who we are to make this newsletter happen? We're a team of professionals and researchers with a lot of experience not only in oil and gas, but as well as in AI applications, so that you can take full advantages of these AI newsletter, guys. Let's get it started. And the first one is GTC 2022 keynote by NVIDIA CEO Jensen Huang, an hour-long event packed with technology that will drive research and innovation over the next couple of years. Without a doubt, graphic processing units are the hardware backbone of the ongoing AI revolution. As a result, it is worth to keep an eye on the state of the cutting-edge technology. This year, NVIDIA debuted the new Hopper GPU architecture and Grace CPU superchip, both of which outperform their predecessor by an order of magnitude. They are also debuted Omni Universe, which is a platform that enables real-time 3D design collaboration in conjunction with physics simulation, resulting in creation of digital twins of real-world objects. The keynote covers a lot of interesting things, so it's absolutely worth seeing. And the next one, how do vision transformers work? The success of deep learning models using multi-head self-attention mechanism is indisputable. In this work, the authors investigate the reasons behind the strengths and weaknesses of transformers. When trained on huge dataset, transformer models frequently outperform convolutional models. Is there a justification for a large dataset size? And why do convolutional networks learn faster? This work attempts to answer these questions by demonstrating that the transformer increases not only accuracy, but also generalization by flattening the loss landscape. This is the UNet and this is transformer. And what is interesting, the authors specifically outperform baseline by substituting some convolutions in a typical neural network with transformers. And the next one is AFNO, a global data-driven high-resolution weather model using adaptive Fourier neural network operator. The authors used a neural network instead of classical numerical methods to accelerate high-resolution Earth-scale modeling. In the area of numerical simulation, transition from a toy example to a large-scale application is a common problem, and this is the problem that the scientists hope to solve by replacing traditional numerical approaches for modeling the atmosphere with an artificial neural network. The study introduces the ForecastNet, a worldwide data-driven weather forecast model that gives accurate short to mid-range global predictions. This effort is an important step towards developing a dependable high-resolution digital duplicate of the Earth. And the next one is the research paper from Geoscience, an unsupervised machine learning applied to seismic interpretation towards an unsupervised automated interpretation tool. As you know, the seismic interpretation process has some drawbacks due to the large volume of data, its complexity, time consumptions, and they introduce uncertainty by our own work. Unsupervised machine learning models which find underlying patterns in data can represent a new way for an accurate interpretation without any reference or label. And you know what is important here? Is that it also removes human biases. Following that, defining the relationship between well logs, including lithographic information and seismic, can provide a more information-rich data for interpretation. The seismic groups that were generated from the field data accurately describes the main seismic features and matches well with the groups that we get from the well-logged data. And the next one is the GitHub account, where you will find a solution for the first break picking problem with machine learning methods. As we know, the travel of first arrival is useful for a variety of applications, including tomographic static corrections, source location, velocity inversions, and many others. Of course, because the reflected signal is heavily influenced by the acquisition, subsurface structures, and signal-to-noise ratio, it cannot be fully automated by traditional techniques. Deep learning can assist in first-arrival picking on field seismic data under these problems. If you want to train your own first-break picking solution based on UNet segmentation, go to Alexey Tarasev's GitHub account. He has provided a complete training code, a pipeline for generated seismic data, and a well-written summary for you. More interesting topics have been covered in previous newsletters as well. I have created a playlist with all of the releases for you. Check them out if you haven't already. Thanks for watching, see you at the next one.